on the screen. And so what I'm going to do is I am going to show you how we do molecular docking. So I introduced this to you in another lecture on drug discovery, but I wanted to show you more in detail. And so rather than do a lecture, I figured what I would do is I would show you this working. So I'm not trying to teach you how to do this. I don't expect you to know how to do this, but you can do this. And what I'm really trying to show you is what are the thought processes that go into molecular docking? What do we need to start and what do we get at the end? And so there are a number of programs that I'm going to use. All of these are free either for general use or for educational use. And so the docking program that I'm familiar with is this doc from UCSF. There are a number of different programs out there. They all have pluses and minuses. A big plus of this one is it's free. This one is primarily for drug screening. And so this is a situation where you have this gigantic collection of molecules that you want to see which ones are likely to bind to the protein you're trying to target. This isn't a situation where you're trying to figure out exactly what atoms in your small molecule interact with what atoms in the protein. That's not what this is designed for. Along with that, from UCSF is a protein called Chimera that we're going to use for a couple of little things. This is kind of a visualization tool and deals with protein structures primarily. The doc program is a Linux program. I only have Windows computers though, and so I need to use a Linux emulator. The one I'm familiar with is Cygwin. Any of them would work. This allows me to run Linux programs in a Linux command line on a Windows computer. You'll see this in action. And then we're going to use PyMol. PyMol is a program that we use to look at three-dimensional structures. So the primary goal of docking is to take small molecules, three-dimensional models of small molecules, and figure out how they bind to a three-dimensional model of a protein. So we need those three-dimensional models. And so we need to download those from online unless you're going to make them yourself, which generally isn't what's going to be happening. So there is a website, rcsb.org, that maintains the Protein Data Bank, or PDB. These are pretty much all of the published crystal structures out there. A crystal structure is a three-dimensional structure of proteins. Any famous protein is most likely going to be in here. So you would pick the protein that you want your drug to target, find the crystal structure, and then download that. I'm just going to pick a random protein. There's no therapeutic advantage to this. I'm just going to pick an oddly named protein. It's easy to remember, and we're going to go with Elmo. Okay. So this is going to bring up all the crystal structures of Elmo. And my Wi-Fi in this room is very slow. Bear with me. So we see that there are, actually, when it does come up, there are 3 of them. You would presumably know in your situation which is the best one, what you want to do. I'm just going to pick this one. The 6IE1 is the structure name. They all have these names. We're going to download this. I need to actually go to the page for the specific one to download the type of file that I need to download. So I'm trying to download a .pdb file. Click link never clicks apparently. Okay, here we go. I'm going to download PDB, and I'm going to save it in a particular folder with Chimera. So it saves it as this. I'm going to rename it something that I can easily remember. I'm going to rename it to elmo.pdb, and I'm going to move it to this particular folder over here. So now it is saved, ready to go, and now I need my small molecule. If you're dealing with a specific small molecule, there are programs that you can use to make a three-dimensional model of it yourself. But what we want to do is we want to screen large numbers of molecules. And so what we want to download what we call a catalog. And there's a website, zinc.docking.org, that maintains these big catalogs. I'm going to click on the catalogs portion. And then they have a number of different catalogs. They have different catalogs for different chemical suppliers like Sigma or Takata or any of those, where you can download all the molecules that vendor has for sale. And so you can say, well, I want to buy molecules from Sigma, so let me only dock molecules that Sigma sells. So what I'm going to show you is a catalog of FDA-approved drugs. So in this situation, we would be repurposing an FDA-approved drug for a new purpose. This is kind of beneficial because if it's already FDA approved, all the pharmacokinetics have already been done, and you can save some work. You can help get it into the clinic faster. If I click on this catalog, we're going to see all of the different molecules that are included. Browse all. It's going to load all of the molecules up here. Notice there's 1,300 to start with. They removed 200 for some reason, and so there's roughly 1,100 molecules here. And then I would save this as a mol2 file. Mol2 is a file name we're going to use over and over. I'm not going to download this because there's 1,100 molecules here, and I'm going to do this docking on my office laptop. If I docked 1,100 molecules, I calculated it would take a couple days to do. And so what I did is I saved a few molecules in a smaller file that we're going to use later on. So that is how you would download your small molecules. So now we can go on to the actual docking. Now, you can't see it because there's no video, but I have written out a protocol for myself. I did it enough times, but I do it so infrequently, I never remember exactly what I need to do, and so I wrote it out. So I'm going to be following a protocol that I have written for myself. Now, the first thing it says we need to do is we need to delete heteroatoms from the crystal structure that we downloaded. That's just elmo.pdb. So I'm going to open that file in a text editor. This is just a text file. That's all it is. And if I scroll down, what you're looking at are the three-dimensional coordinates of all of the atoms in our Elmo protein. Now, what I want to point out is you see it says atom here. What we want to do is we want to delete anything that says het atom, standing for hetero atom. In most situations, these are going to be waters that are part of our crystal structure, but we don't want them when we do our docking. So I'm going to find where the atoms change to heteroatoms. There it goes. So we see it says atom, there's a termination, and it switches to heteroatom. So I'm just going to select all of the heteroatoms, delete them, and resave my file. We don't want those heteroatoms being in there. The next thing I need to do is I need to prepare the protein for docking. And I'm going to do that using the Chimera protein. So I downloaded it from the website, I opened it, I'm going to open elmo.pdb, and we're actually looking at the three-dimensional crystal structure of Elmo. So I'm going to follow my directions that I wrote myself. It says I need to show the surface by going Actions, Surface, Show. So now we're seeing the electrostatic surface of the protein. Now I need to save this as a different type of file by going to Tools, Structure, Editing, Write DMS. I'm going to save this as elmo.dms. Also in Chimera, I need to prepare the proteins in other ways. And so I'm going to go to Tools, Structure, Editing. Normally you just use the defaults, but we need to make sure that we have add hydrogens and add charges checked. Make it okay. You can see it's doing things. This takes a second. We just have to wait for it to do what it's doing. It says not responding, but it will come back to us. While it's doing that, I can show you we can also open our protein in our PyMol. So this is what our protein is going to look like in PyMol. So what I did is I showed surface. If I hide surface, we see something like this. But we don't care necessarily about individual atoms. What we care about is the surface. So I want to show surface. Different colors represent different elements. So we're going to use PyMol a lot, so I'll come back to that in just a bit. So I'm going to hit OK on Chimera. Hitting OK. Now I'm going to save this as elmo.mol2. Now we're done with Chimera. I'm just going to close it. So now we made the surface. What we need to do is we need to tell the program where on that surface we want to dock to. So this is where we're going to start using Cygwin, which is the emulator, and using Linux commands. Again, I do not expect you to know these commands and don't understand what I'm doing. That's why I wrote them down for myself so I can just type in what I told myself to type in. First thing we need to do is we need to make spheres. Spheres are going to tell the docking program where to dock to. So we're going to use a program to do that. In order to do that, I need to go into a specific folder within Cygwin. That's what I'm doing here. Now we're in the folder, the doc6 bin folder, that we're going to do the docking in. That's where all of these files are. And I'm going to use a program called SphereGen in order to make the spheres to go with it. Some very basic Linux commands are telling it to use the SphereGen CPP program with the input of our elmo.dms file, and I want to make a new file, elmo.sph, for sphere. It is currently finding all of the places on that surface where a small molecule could bind. It's going to put a little sphere there. So that's what it's working on now. So we did that. We want to see where these spheres are. And so I want to open this in PyMol. But PyMol can't open a sphere folder, a sphere file. We need to convert our sphere file that we just made into a PDB file. So I'm going to do that using another program called show sphere. And so I want to use elmo.sph. That's what I'm converting from. I want to make a file called sphere.pdb. So it made a file that we can open in PyMol. So I already had a couple things open. So let me open that sphere.pdb file that we just made. I'm going to tell it to show it as spheres. So now you can see all of the spheres that it made, but it made spheres all over this protein. If we told the docking program to dock to these spheres, it would take forever because it's going to try to dock everywhere on the protein, which isn't what we wanted to do. We wanted to dock to a specific place on the protein. So first thing we need to do, we have to figure out where do we want to dock to. So let me hide these spheres for a second, and let's look at our protein. Ideally, you would be familiar with the protein you're docking to, and you would know specifically where you want a small molecule to bind. Now, I know absolutely nothing about Elmo. We're not actually trying to create a drug. So I'm just going to pick a spot, and if we look, there's like this odd Mickey Mouse-shaped window here. So let's say we want to find a small molecule that binds and sticks in this little window here. So we want to delete all of the spheres that are not in that window. Now, you could go through and delete every single one of them manually. Luckily, we don't have to. if we go into back to our SIGWIN, we have a program called sphere select that is going to allow us to delete every sphere that is greater than a certain distance from where we want to dock to. But we need to tell it where we want to dock to. And we're going to do that by telling it an atom number in our protein structure. So we need to find somewhere in this gigantic file what atom number we want to dock to. So I'm going to go back to Pymol. I'm going to hide the spheres. And actually, I'm going to hide the surface. Did I do? I don't know what I did. So I'm going to show sticks and hide surface. So now we can see individual atoms here. Now I lost track of where my window was, so I need to show my surface again. So there's my window. So notice there's this little bump that sticks down into our window. I'm going to say that is the center of our docking location. Okay. So I want to figure out what is the atom that is right there. If I click it, it doesn't tell me the atom number, but up here it tells me that I am looking at asparagine 332. If I go back to my PDB file here, I can find asparagine, what was the number? 332. I'm going to scroll down so I get to asparagine 332. Now I'm just going to pick one of these atoms that's in asparagine 332, and 2540 is an easy one to remember. So we're going to tell it to delete all the spheres further away than a certain distance from atom 2540. So here, program sphere select. The input is going to be my Elmo.sph. The radius that I'm looking for is 12 angstroms from atom number 2540. And that atom number is in our file, elmo.pdb. And I want to make a new file, sphere select.sph. Now, this is just a naming convention I made for myself so I can keep track of the different iterations of spheres. You can name these anything that you want. So it says here that it saved 33 spheres, sphere select.sph. What I'm going to do is I'm going to again convert our SPH file into a PDB file so that we can look at it in Pymol. Again, remember, I'm typing in what my instructions tell me. So now we've made that. Let's look at it in Pymol. Let's turn our surface back on. So now you notice. Oh, hold on, just a second. You notice that it deleted all the ones that were a long ways away, right? But we still have a bunch of spheres here that are not in our window. And so if we do the docking with these spheres that are currently here, we're liable to end up with a molecule that's down here or up here rather than being in our window. And so we again need to delete all the ones that are not specifically in our window. This one we have to do manually. Okay. So what I'm going to do is I am going to click and delete individual spheres that don't exist in our window. I'm not going to make you watch this. I'm going to pause the video, delete that, and then come back. Okay, so I deleted all of them. And so now you can see that there are spheres only in our window. Okay, after I did that, I came up and I went through export molecule and saved it as sphere selected.adb. So again, I have sphere to sphere select, to sphere selected, and that all started from elmo.sphere. And so I know where in the stream or the string each one of these belongs. Now the docking program uses SPH files, not PDB. And so we need to get an SPH file that only contains the spheres that are currently here in our PDB file. So if I open our sphere select.sph file, we see these are the 33 that our program initially gave for us. And if I open my sphere selected.pdb, you see a much smaller list. So what I need to do is I need to delete anything that's in this list that is not in this list. Now I already did that. I did it manually. If you're someone who knows Python, you might be able to write a quick little program to do it, but I don't. And so I did it manually. And so I now have a sphere selected.sph file that contains only the ones in my PDB file. And there were 12 of them. And so one thing I want to point out, if you do actually try this yourself, this number originally said 33 because our program picked up 33. When I deleted some, I now only have 12 left, and I need to change that number to 12. If you don't, you're going to get an error later on. So I then save this as sphere selected.sph. Okay, so I'm actually going to stop right here for this video. I'm going to just save it and come back in a second video, and we're going to actually do a little more docking prep and then do the docking.